All right, in this video, we're going to take a quick look at how to name and determine formulas for polyatomic ions. Um, uh, so basically, we're just going to look at the crisscross rule for ionic compounds containing a polyatomic ion. Now, just a quick recap, a polyatomic ion is a group of nonmetals that are bonded together that carry an ionic charge. This group of nonmetals stay stuck together in bonding. You kind of have to consider that it's just one thing that carries an ionic charge and that will crisscross. The ratio of nonmetals that are bonded together in this polyatomic ion stays the same. And it never changes unless it's undergoing a chemical reaction. It can undergo a chemical reaction and become a different polyatomic ion. But because this group of nonmetals carries an ionic charge, it can bond with a metal to form a polyatomic compound. Now, I like to focus on what I call the eights. These are the most common polyatomic ions that you're going to start working with, and I have them written out here. Carbonate, phosphate, chlorate, fluorate, bicarbonate, nitrate, sulfate, iodate, bromate, and the odd man out, hydroxide, which is not an 8 because it's hydroxide, OH negative, but important enough and used very often in chemistry that it's worth including it in this list. Now, on the periodic table that you are going to have and use for this course, there is a table of complex ions at the top. And some of these eights are listed there. You don't even have to memorize them. However, it's going to be in your best interest if you, as you are learning and working with these, you do actually know by memory the formulas and charges of the eights. It will serve you well if you can just recall them, like you can recall common element symbols. So we're going to take a look at how to use the crisscross rule to write the formula if you have the name of a polyatomic compound. Remembering that the crisscross rule is just a shortcut to figure out the number of each ion that is needed to result in the overall charge of 0, a neutral charge for the compound. So the first one we're going to look at is calcium phosphate. So our calcium phosphate, same rules as before, right? The symbol of each of the ions involved, so calcium, and then phosphate up here in our chart, we can see if we look right here, is PO4, and then we write our charges. Our phosphate is a 3 negative, and our calcium we know is a 2 plus. So same rule or process as before. We drop the charges and we cross the numbers down. So if we do that, we're going to end up with Ca3 and then PO4 and then the 2. Now, if we leave it like this, it looks like we have a phosphorus, an oxygen, or phosphorus and 42 oxygens. But that's not the case. We actually have 2 of the phosphates. So what we do is we're going to use a bracket when there is more than one polyatomic. So if you have more than one of these polyatomics, you have to put a bracket in because now this 2, because it's outside of the bracket, is telling us that we have 2 PO4s. Without the bracket, it looks like you have one phosphorus and 42 oxygens. Let's do another example. Oh, I don't want to write in orange. So sodium hydroxide, writing the symbols and the charges. Sodium has a charge of +1, and hydroxide has a charge of -1. So actually, I wrote those backwards. So then we crisscross them. This one comes here, this one comes here, and we end up with Na1, but we know that we don't write the 1, and OH1. So just want you to note that we don't have a bracket. So we're not going to use a bracket when there's only 1. So there's only 1 hydroxide, so we're not going to use our bracket here. Okay, we're going to do 2 more. So now let's look at copper 2 sulfate. So same rules, write the symbol Cu and the charges. We know because it's copper 2, then this has a charge of 2+. And we can look up our sulfate in our list of polyatomics for today, and it's SO4 2-. So we take our numbers, drop the charges, cross them down, and we end up with Cu 2 SO4 2. But because both of these are a 2, we can put it in lowest terms, and we divide them both by 2, so we end up with Cu SO4. So just remember that the rules for multivalence are the same, regardless if they're bonded to a polyatomic ion or just a single nonmetal. The Roman numeral still gives you the charge. And when you're naming, you have to use a Roman numeral. So when you are determining the name for a polyatomic compound from a formula, you still have to do a quick check for the multivalent metal. So let's do a couple examples where we're going to have a formula with a polyatomic and name it. So just to recap the rule, write the name of the metal first, check for multivalent metal, do a reverse crisscross to determine the Roman numeral, and then just name the polyatomic. So let's take a look. We have Zn bracket NO3 bracket 2. So name of our metal, Zn, zinc. Do a quick check. Zinc is not a multivalent metal, so we do not need to figure out its charge. And then the name of the polyatomic, NO3, we know is nitrate. So this is zinc nitrate. Let's do another example. We're going to do PB bracket ClO3 bracket 4. So looking at our rules, first part of our step, name of our metal, PB is the symbol for lead. Lead is a multivalent metal, so we have to do a reverse crisscross. This 4 comes up here and becomes the charge for lead. And the invisible 1 comes up here and becomes the charge for the chlorate. So at this point, you have to do a little check. Is the ionic charge of chlorate 1 minus, -1? Yes, it is. So this means that this formula has not been reduced. So the Roman numeral for lead is 4, and then ClO3 is chlorate. Let's look at another one. This time we're going to look at AlPO4. So in this example, we are going to do name of our metal, Al, aluminum, and name of our polyatomic PO4 phosphate. Now you might say, wait a minute, doesn't phosphate have a charge of 3 minus? And I will say, yes, it does. Because what has happened is this has been reduced. This was a 1. And this invisible comes up here. But we know that aluminum has a 3 plus charge and the phosphate has a 3 minus charge. So this is an example of a formula that has been reduced. Thankfully, it's not a multivalent metal, so we do not have to figure this out for a Roman numeral. All right, one final example. Oh, wrong color. Cu SO4. So Cu, symbol for copper. Copper is a multivalent metal. So we have to figure out the Roman numeral for our copper, and we're going to do a reverse crisscross. So this is an invisible 1, and it is going to cross up here, 1 minus. Now over here, there is also an invisible 1, and it is going to come up here, 1 plus. I want to caution you that you do not accidentally crisscross this 4. That 4 is attached to the oxygen. It is not the subscript telling you the number of sulfates that are there. So if we do a reverse crisscross, we can see that we have copper with a charge of +1 and a sulfate with a charge of -1. The problem is if we look up here, we're going to see that sulfate actually has a charge of 2 minus. So we have to turn this into a charge of 2 minus. And we're going to do that by multiplying both of these charges by 2. This formula has been reduced. So if we multiply this 1 plus by 2, it becomes a 2 plus, and this becomes a 2 minus. So now the polyatomic has the correct ionic charge, and our copper gets the Roman numeral 2. And then SO4 for our sulfate. Okay, so this is just, these are not the only polyatomics we're going to be working with, but this is the starting point, our 8s. So just get comfortable doing reverse crisscrosses to get the correct Roman numeral from when you have a transition or multivalent metal bonding with a polyatomic. Be careful that you are not doing things like crisscrossing this 4 that's part of the polyatomic. Okay, so that is it for now. You're just going to have to do some practice with this, get better at polyatomic nomenclature, and we will move on with nomenclature in another lesson.